At the next crater, turn left. Turn left. Oh, geez. What's up, you scholars of enlightenment? The European Space Agency, or ESA, is proposing a high-precision navigation system on the moon. The system would enable spacecraft and astronauts to know exactly where they are when moving towards a lunar body, to land with precision, and also to bring the beauty of Zoom and Skype to the moon. For fuck's sake! It's much like the sat-nav system here on Earth, and that got me thinking, because I'm a little bit odd like that. What would happen if you took the sat-nav out of your car here on Earth and used it on the moon? How accurate would it be? Well, to answer that question, we first of all need to know how sat-navs work, because your sat-nav uses the GNSS, or Global Navigation Satellite System, to work out exactly where you are on the Earth. And this clip from the excellent channel Some Stuff Explained, go and subscribe immediately over there by the way, explains how such positioning works.
GPS is not just one satellite, but actually a network of up to 32 satellites, orbiting the Earth 20,000 kilometers above ground. That way they are always a few above you. These GPS satellites are basically atomic clocks with a radio and solar panels, constantly sending signals back to Earth. Each broadcast contains the current location and the precise time the signal was sent. And even though these broadcasts travel at the speed of light, it still takes between 50 and 100 milliseconds for them to reach the Earth. A GPS receiver listens to all of these signals, but because some satellites are further away from you than others, their signals arrive at different times. So when satellite A and B send out a signal saying that it's exactly 12 o'clock, but the signal from satellite A gets to you first, then you have to be closer to satellite A than B. Your GPS receiver can measure the precise time between the two signals and calculate how much closer satellite A is. Because the satellites also send out their current position, you not only know where you are in relation to the satellites, but where you are exactly. Add a third satellite and you can get coordinates in a two-dimensional space, or a map, and with a fourth you can also calculate elevation. And with a system like that, you can pinpoint your exact position on Earth with an accuracy of up to 1 meter.
But of course, satellite range measurements, much like Chinese lab security protocols, aren't necessarily perfect.
You calling us cunts?
Your distance from an individual GPS satellite can only be known to a finite accuracy due to multiple real-world effects, such as errors in GPS satellite time synchronization, errors in measuring the exact positions of GPS satellites, atmospheric refraction, and other factors. What that means is that the signals from GPS satellites form fuzzy, spherical ranging shells, or circular arcs on the Earth's surface, with a finite thickness of several meters. And your distance from a given satellite can only be fixed to somewhere within that shell. Even if you stand completely still on the Earth, your position, according to GNSS, GPS, will wobble back and forth within that shell. Now, despite these errors, Earth-based sat-nav positioning can be highly accurate because there are so many GPS satellites in orbit, and hence signals are reaching your sat-nav from many different directions in the sky. These overlapping signals constrain your sat-nav, and therefore your car or phone, to be within a small projected area on the Earth's surface, the green box. Indeed, a commercial sat-nav can pinpoint your location on the Earth to within a box of around 10 meters squared under optimal conditions. That's pretty impressive stuff.
Impressive.
The problem with trying to use a sat-nav on the moon, apart from the fact that you need a massive dish to detect the weak signal, the choking, the lack of food and water, the radiation, the low gravity, is that GNSS position fixes are not only sensitive to the range errors of the satellites, which we've talked about, but they're also very sensitive to the satellite and receiver geometry, an effect known as dilution of precision. Imagine if instead of having satellite signals converge in a receiver from different directions, as they do here on the Earth, the signals from all satellites all came at us from the same direction. Instead of the signal arcs from two satellites overlapping to form a small precise area and hence give an accurate position fix, they are now largely parallel at the receiver and overlap over a far greater area. What that means is that the position of the receiver can only be nailed down with far less precision. And in one dimension, that means that we can only say our receiver is somewhere between the two extremes of that green arc. This is the same dilution of precision effect that GPS receivers experience when you enter an enclosed space like a canyon or travel between tall buildings. All the GPS signals you're receiving are funneled into a narrow corridor, and your GPS locator or sat-nav becomes less accurate. The dilution of precision, or DOP, increases. This overlap and the dilution of precision only gets worse as the receiver moves away from the satellites along a common axis. And now, enter the moon, which is pretty far away.
You smart.
Here's our planet, as seen from a beautiful sat-nav using colony on the moon around 400,000 kilometers away. Earth's GNSS satellites orbit our planet at a height above the surface of around 20,000 kilometers or 26,000 kilometers from the center of the Earth. So from the perspective of our lunar colony, all the satellites are transmitting from a very small patch of the sky. They are almost all transmitting along the same axis. And as we saw previously, that's very bad for precision. Now, GNSS satellites fire their signals directly down onto the Earth, but they have a finite signal width that means that signals can likely be detected as much as 40 degrees from the signal axis, and therefore probably at the moon. Using some very simple geometry, that means that the widest angular separation between GNSS satellites, as seen from the moon, is about 3 to 4 degrees. It seems that all of our GNSS satellites are transmitting within a canyon of about 3 to 4 degrees angular separation. Now, according to my tech guru colleague, in order to calculate the dilution of precision on the moon, i.e. how much worse a sat-nav would perform on the moon compared to on the Earth, we need to, and I quote, take the Euclidean distance of a subset of the diagonal elements of the matrix that results from taking the Moore-Penrose pseudo-inverse of the square of the unit vector matrix. Fuck that. Let's go back to our overlapping rectangles.
Sonny, we can do this the easy way or the hard way.
The easy way.
Now imagine the signals from two satellites projected onto the surface of the moon. They form two overlapping rectangles with a thickness of roughly 3 meters. That's the inherent ranging accuracy of the GNSS system. And they're offset by about 3 or 4 degrees with respect to one another, that angular window of the satellites in the sky. Now imagine a sat-nav, your car or your phone, stationary on the moon. At a particular time, satellite 1 can give a range measurement for the sat-nav at its maximum upper limit, while satellite 2 gives a range measurement for the sat-nav at its minimum lower limit. The point where these two measurements overlap is the position of our sat-nav, our car or phone, according to the two satellites. It's at this position. But remember, even if our sat-nav never moves, the range measurements of the satellites wobble around in time. And that means that a moment later, satellite 1 may return a range measurement for the sat-nav, now at its minimum lower limit, while satellite 2 returns a range measurement for the sat-nav at its maximum upper limit. The point where these two measurements overlap, the position lock of our sat-nav, now jumps around by as much as 120 meters, despite our sat-nav never having moved. Therefore, all we can say is that our sat-nav, our car or our phone, is somewhere within that 120 meter wide region. And this is our estimate for the very best one-dimensional positional lock that a commercial sat-nav could make on the moon, to within about 120 meters in any direction, or about 40 times worse than the positional lock accuracy you can get on the Earth. a dilution of precision of about 40. So sadly, your sat-nav ain't finding Starbucks on the moon, although Starbucks is a pretty good name for a coffee shop in space.
Yeah, that's true. That's true. That's true. That's pretty true. That's pretty true. I mean, that's true. Yeah.
And by the time your sat-nav tells you to avoid the next moon crater, you're probably already in it. At the next crater, turn left. Turn left. Oh, geez. Now, believe it or not, that simple geometric approach that we took actually gives results that are roughly in line by those calculated accurately by experts in the field. Complex simulations that calculate the dilution of precision at lunar distances accurately by projecting the orbits of all the GNSS satellites around the Earth calculate the best dilution of precision at the moon of around 40, and the best 1D position locks you can achieve on the moon of about 200 to 300 meters, very much in line with what we calculated. So, even with a crappy order of magnitude estimate, we didn't do too badly.
Not bad.
Thank you, Mr. President.
Not too bad at all.
But remember, our estimate is a best case scenario. GNSS satellites are constantly orbiting the Earth, so it will be rare that satellites are as widely and perfectly spread as we assumed in our calculation. We've also assumed that a sat-nav can detect a GNSS signal at 40 degrees from its signal emission axis. This is a very optimistic estimate. If the angle is less, then the satellites will be closer together and our lunar positioning will get even worse. So it's kind of cool that using that Earth-based GNSS system, you could know where you are on the moon to within a few hundred meters. But it's worth noting that even if you want that diminished level of accuracy, you really need the stars, or at least the satellites, to align.